Welcome to our session focused on the quantum Hall effect. Today, we are going to see how quantum Hall effect appears in materials, and in particular, how we can understand the physics associated to the quantum Hall state. And perhaps one of the most important points to understand at the beginning is that the quantum Hall state is a state of matter that appears in many different materials. It can be found in semiconductor, quantum wells, gallium arsenide quantum wells. These were one of the most popular platforms to see quantum Hall physics. And in these cases, the energy scale of the quantum Hall state is roughly proportional to the magnetic field. And this gives rise to a required temperature to observe quantum Hall physics on the order of 1 Kelvin. Most interestingly, the quantum Hall state can also be observed in two-dimensional materials, and in particular in graphene. And one of the very special points that we will elucidate later on is that in graphene, the quantum Hall energy scale depends on the square root of the magnetic field, and this different dependence effectively makes the quantum Hall state in graphene appear at much higher temperatures, and in particular, it can be observed at around 100 Kelvin and even up to room temperature. Independently on which platform we focus, quantum Hall state has many common features, and in particular, one of the most important ones is the quantization of the conductance that we already briefly discussed in the previous session. So, to understand the quantum Hall state, perhaps the most interesting and important experiment is to understand the quantum Hall conductance. This is the conductance that we observe when we take a two-dimensional system and we apply a gate in one direction, we apply a voltage in one direction, in particular the y direction in this scheme, and then we measure a current in the x direction. And when we do this, the relationship between the voltage that we apply and the current that it's observed is given by the Hall conductance, which is the object that gets quantized in the quantum Hall state. From an experimental point of view, the typical quantum Hall devices have the following form. So you have a two-dimensional electron gas, and then you have usually 4 different finger gates, and you can apply voltages between one of the top and the bottom ones, and then measure the current in between 2 of the gates that you have in the x direction. And in this way, you can effectively measure, let's say, the current that appears in a direction that it's perpendicular to where the voltage is applied. And if you think about a real device, one usually has something like this. So you have a two-dimensional electron gas that can be a two-dimensional material, and then these different finger gates are connected to some metallic leads, and one applies the voltage in those metallic leads. Okay, let us move on now to understand the origin of these quantized conductance. If we use just perturbation theory, if we use the Kubo formula to compute the whole conductance, what you can actually see is that you can essentially write down the conductance as a function of the derivative of the Hamiltonian with respect to different momenta, and you need to consider all the wave functions of your Hamiltonian and also the energy differences. This is the formula that appears directly from using perturbation theory to the definition of the quantum Hall conductance. And one of the most important points is that this object that comes from perturbation theory can actually be understood as the very curvature of a band, and in particular, the quantum Hall conductance is computed as the integral of the very curvature over all the occupied bands. And this can be seen explicitly by making the replacement of the derivative of the Hamiltonian with respect to the momenta as a function of the derivative of the wave functions. And this is a formula that you can directly obtain just by taking the definition of an eigenfunction of a Hamiltonian and applying the derivative. If you take this identity and you plug it in the definition or the formula of the quantum Hall conductance, what you actually observe is that the Hall conductance loses its dependence on the energies, and it only depends on matrix elements between wave functions. And in particular, the quantum Hall conductance can be written in terms of the very connection and the curl of the very connection, that is the very curvature. And if you take these 2 objects, the very connection and the very curvature, what you see is that they only depend on the wave functions themselves, and there's no dependence at all on the eigenenergies. Once you take the very curvature and you integrate it in the whole momentum space and you sum over all the occupied bands, you effectively get the quantum Hall conductance, and this quantum Hall conductance is effectively the same as the Chern number. The quantum Hall effect is one of the very specific states where an observable, that is the Hall conductance, is directly a topological invariant, and in particular, the Chern number. And the idea of the quantum Hall state is that in the presence of a magnetic field, a two-dimensional electron gas develops a set of flat bands, that later on we will call Landau levels. And each flat band has a dispersionless energy versus momentum relation, because of course it is flat, but it also has a finite Chern number. So it has Chern number 1. So if you have the chemical potential, for example, in between the second and third bands, then the total Chern number of your system is the Chern number of the first band and the Chern number of the second band. And overall, you essentially have a Hall conductivity that is proportional to the number of flat band Landau levels that you have filled, and in particular, that it's actually an integer and it is quantized. Of course, one of the most important questions of the quantum Hall state is, if we have an insulator, if we have a system where the chemical potential is in between two bands, how can we have a finite conductance? This, of course, a very subtle and really fascinating question, but the simplest explanation to the existence of finite conductance comes simply from the existence of H states. So you can actually recall from the previous session that if you have a system that has a finite Chern number, then at the interface between the system and vacuum, you are going to have a topological mode. You are going to have a protected mode that is chiral, and you are going to have as many modes as the difference in Chern numbers between vacuum and your material. If you think that vacuum has Chern number 0 and your material has Chern number 1, then you will have one H state. If your material has Chern number 3 and vacuum has Chern number 0, then you will have 3 H states. The important point is that in a real experiment, your system is always finite. Your system always has some boundaries, some edge. And at the edges of the system, H states are going to appear. Chiral states are going to appear. And now when you apply a voltage, that can be a difference in the chemical potential between the bottom edge and the top edge, then you are creating more right-moving electrons than left-moving electrons, and that gives rise to a quantized quantum Hall conductance. If we think in terms of the band structure of the quantum Hall state, perhaps the simplest way of understanding this coexistence of Landau levels at H states is by considering a ribbon that in this picture is infinite in the y direction and computing the band structure. And this is something that we will do later on. But overall, what you are going to see is that you have states that are located on the left edge that propagate in the in one direction, that are the red states that you see here in the plot in the bottom left. And then you also have states that are propagating in the, let's say, right direction, and that are located in the opposite edge. And these states are the ones that are in blue, and you effectively see that the states that propagate in one direction are located in one edge, the states that propagate in the opposite direction are located in the other edge. And this separation between the location of the state and where and to which direction it's propagating is essentially what gives rise to the quantization of conductance. You can imagine that if you take a state that is on the left and you put an impurity, then an electron cannot scatter to the right because the right is very far. So electrons that are moving on the left, they can only keep moving on the left, and electrons that are moving on the right, they can only keep moving on the right, and most importantly, in the same direction. So you don't have any sort of, let's say, resistance. You don't have scattering events that are capable of creating backscattering. So let us look now at how this actually looks like in a real experiment. So if you take a conventional two-dimensional electron gas and you start applying a magnetic field, what you will observe first is that at very low magnetic fields, below the magnetic field required to enter in the quantum Hall state, you have a Hall resistance that is proportional to the magnetic field. This is just classical magnetoresistance that you know from electromagnetism. Then once you go to relatively high magnetic fields on the order of 1 Tesla or 10 Tesla, depending on the specific material, then you see that a set of steps appears. And this set of steps are essentially dependent on the Hall conductance, on the quantum of Hall conductance. And these steps essentially tell you how many Landau levels you have filled. So at moderate magnetic fields, you have a certain set of Landau levels, and as you increase the magnetic field more and more, then your chemical potential starts traversing Landau levels, and every time you have less Landau levels filled. And therefore, in the quantum Hall regime, you have a quantization of the conductivity that gives rise to a quantization of the resistance, and that is the origin of these steps. Okay, this is effectively phenomenology of the quantum Hall state. Now, what we are going to focus on is on understanding how the wave functions of the quantum Hall state are, and in particular, how the mathematical structure of these wave functions actually brings up all these topological properties. So perhaps the simplest way to start is just by recalling how classical electrons get coupled to a magnetic field. So the basic idea is that if you try to write down a Hamiltonian for an electron coupled to a magnetic field, you need to define something that it's called a vector potential. So a potential whose curl is the actual magnetic field, because once you put this onto your Hamiltonian, then by finding the equations of motion, you essentially recover the equations of electromagnetism. And the way this is included usually in the Hamiltonian is by defining what is called the canonical momenta, which consists on taking the original momenta, that it's P, and adding the magnetic vector potential. If you do this replacement on your Hamiltonian and you compute the equations of motion, you will obtain the conventional classical equations of motion of an electron in a magnetic field with the Lorentz force, as we are familiar with. We can use the very same trick in quantum mechanics. So we use this canonical replacement. So we replace the momentum by P plus A in our Hamiltonian that now is a quantum Hamiltonian. And what we have to do simply is to now solve a differential equation with P and A, just by recalling that P is now the derivative with respect to the position in real space. Now, one very important point is that there's not a unique magnetic vector potential. There are several magnetic vector potentials that give rise to the same magnetic field, just because you can just add the gradient of a certain function in real space, and when you compute the curl, you recover effectively the same magnetic field. So for us, there's going to be two important gauges. There's going to be the symmetric gauge, and there's going to be the Landau gauge. So the most important point at this stage is to note that this dependence on the magnetic field can be included either in the Hamiltonian or in the wave function itself. You can actually do a local gauge transformation that transfers all the dependence of the magnetic field directly to the wave function. So for, let's say, solving electrons in a magnetic field in the continuum model, we will effectively include the magnetic field in the Hamiltonian. For solving a tie-bonding model, we will include the effect of the magnetic field directly in the wave functions themselves. And this is essentially the point of how we can include magnetic field in a tie-bonding model. So let us imagine that you start with a tie-bonding model that takes the form Tij C dagger I Ca. Maybe the first question in terms of a magnetic field would be, well, how can we include the dependence of the magnetic field inside this tie-bonding model? So the basic idea is that you can, let's say, put all the dependence of this magnetic field, and in particular the vector potential, onto your wave function. And when you do that, you can just see how the hoppings get renormalized by the magnetic field. So by definition, the hopping Tij is essentially the overlap between the wave function inside I, your Hamiltonian, and the wave function inside A. And if you now put the dependence on the magnetic field inside the wave functions I and J, what you actually end up is with a hopping that it's essentially renormalized by a prefactor that it's a complex phase that comes from the integral between Ri and Rj of the magnetic potential. So the formula that you have at the very bottom. Again, this replacement is a replacement that you automatically get once you put the dependence of the magnetic field entirely on the local wave functions, and you look at what is your actual definition of the hopping in terms of matrix elements. Okay, wonderful. So we have two different ways of including a magnetic field. We have this, let's say, canonical replacement, where we take the original momentum and we replace it by P plus A. As we mentioned before, this is especially useful when working in a continuum limit. And this actually means that we are taking Schrodinger electrons or Dirac electrons, and we will try to solve the Schrodinger equation, just the differential equation of the electrons. And then we have the other alternative, which is to put all the dependence of the magnetic field directly onto the wave function. And this is a methodology that is useful if you are working with die-bonding models. So effectively, you just need to replace every single hopping by the hopping times a phase, and this phase is essentially the circulation of the magnetic potential between locations I and locations J. And this is what it's usually called the Peierls substitution. Okay, to understand Landau levels, which are the flat bands of the quantum Hall state, it is useful to do it directly with a continuum model, and that is what we are going to do now. So in general, the electronic structure of a quantum Hall state looks like the picture that you have on the left. So you have a collection of flat bands. These flat bands are can be labeled by an index n. So you have n equal to 0, n equal to 1, n equal to 2, n equal to 3. And n essentially tells you what is the index of the Landau level. So you have the first Landau level, second Landau level, third Landau level, and so forth. The energy scale of these levels is what it's called the Landau level energy. And for a two-dimensional electron gas that has a parabolic dispersion, so that it is governed by an energy dispersion that is v squared over 2m, then the typical energy scale of it's n plus 1/2 of the magnetic field. So it's linearly proportional to the magnetic field, and the different Landau levels are equally spaced. If you take all the physical constants that should be in that formula and see what energy scale you get, you will see that you get around 1 milli-electron volt of energy scale, which is essentially the energy scale that you need so your temperature needs to be substantially lower than this energy scale in order to see quantum Hall effect. If you use the same idea, but now with the Dirac equation, so you no longer assume that you have parabolic electrons, but you assume that you have Dirac electrons, as it happens, for example, in the honeycomb lattice, which is, of course, the electronic structure of graphene, then what you get is that your energy scale is substantially bigger, and depending on how you make the estimate, you get to something on the order of 100 milli-electron volts. So let's say almost 2 orders of magnitude higher than the energy scale that you have for parabolic electrons. And this different dependence comes from the fact that now the energy depends on the square root of the magnetic field instead of being linearly proportional to the magnetic field. And apart from that, instead of having n plus 1/2 energy spacing, you have an unequal energy spacing that goes as the square root of n. Okay, so now we need to solve the Schrodinger equation with a magnetic field. And at this point, we need to consider which exact gauge we are going to be working with. So as you know, we are going to focus on the case where the magnetic field is completely perpendicular to the sample. So the magnetic field is 0, 0, BC. There are several gauges that give rise to this magnetic field. And in particular, there are several magnetic potentials whose curl is the magnetic field. There are two of them that will be very important for it. The first one is Landau gauge, which is a gauge where you put all the spatial dependence on a single coordinate. So the one on the left, which is minus BC y. And the deal of this gauge is that it respects one translational symmetry of the Hamiltonian. So your Hamiltonian no longer commutes with Py because you have a y dependence in the magnetic potential, but it commutes with Px because there's no x dependence in the magnetic potential. This is a very subtle and very important point of the quantum Hall state. When you apply an out-of-plane magnetic field, you would say that you are not breaking any in-plane translational symmetry. But when you try to include the magnetic field in the Hamiltonian, just from the fact that you have to choose a very specific gauge, you will break a translational symmetry because the gauge that you choose is going to either break translational symmetry in X or translational symmetry in Y or both. The Landau gauge is the gauge that only breaks the translational symmetry in one direction, so that we can still talk about the band structure, at least of a one-dimensional system. And this type of gauge is, for example, the gauge that we use in tie-bonding models when we look at ribbons. And then there's another very important gauge, which is the symmetric gauge. The symmetric gauge breaks both translational symmetries in the system. So the Hamiltonian no longer commutes with Px, no longer commutes with Py, but it has the very special property that it treats X and Y on the same footing. So it conserves the rotational symmetry of the Hamiltonian. And this gauge is going to be the most useful gauge to write down the many-body wave function of the quantum Hall state, the many-body wave function of the Landau levels, and in particular to understand the emergence of fractional excitations in the quantum Hall state. Okay, so let us then move on to solve our Hamiltonian. So the basic idea is that we are going to consider the simplest case where we only have kinetic energy. So there's no potential at all. We just have free electrons in space in the presence of a magnetic field. So the net Hamiltonian for a conventional to the electron gas, for a quadratic to the electron gas, is going to be p squared over 2, or when we do the canonical replacement, pi squared over 2. And in practice, is going to look like the derivative plus the magnetic potential to the second power over 2. This is what comes from the minimal gauge coupling. This is what comes from the canonical momenta. And so now the trick is that we just need to find the eigenstates of that Hamiltonian. We need to find which states are diagonal for that Hamiltonian. And the idea is quite simple in order to solve this problem. So if you take the Landau gauge, you effectively get that the only dependence that you have of the magnetic potential is in the x coordinate, for example. So you have a magnetic potential that looks like 0 minus Vx and 0. If you just expand the quadratic Hamiltonian that you have, you will see that the Hamiltonian has a term that it's px squared, and that it has another term that it's x squared. And it has another term that it's linear in x, but you can reabsorb it using a change of variables. So in practice, you have a Hamiltonian that has p squared and x squared, which is effectively a harmonic oscillator. It is just the very same Hamiltonian as the quantum harmonic oscillator. And then you can solve this Hamiltonian just using the very same tricks as for the harmonic oscillator. So you can define your ladder operators, for example. And when you do that, you see that the energy is essentially proportional to an integer times the frequency square. And you effectively get that the energy of the Landau level is n times b. Okay, so this is one of the most important points of the quantum Hall state. Electrons in a magnetic field behave as a harmonic oscillator, at least in the case of a Landau gauge. So this is the reason why the Landau levels are equally spaced for a quadratic Hamiltonian, and essentially this comes automatically from this linear dependence that we have in the magnetic field potential. Now the next point that we can deal with is the Landau levels in the Dirac equation. And so the Dirac equation is essentially relatively similar to the Schrodinger equation, but now instead of having p squared, we have a matrix where we have px and ipy in the off diagonals. And for this Hamiltonian, we can do again the canonical replacement. We can replace the momentum by the momentum plus the magnetic potential. Again, we can take the gauge where the magnetic potential only has dependence on x, which is the Landau gauge. And now the trick is that our Hamiltonian is now a off-diagonal matrix, but the Hamiltonian square is now a diagonal matrix. And when you compute the Hamiltonian square, just by, let's say, brute force multiplication of the Hamiltonian that you have on top, what you actually get is that your Hamiltonian square is proportional to p squared plus b squared x squared plus a constant term that you can reabsorb. And in practice, you get that your energy square is essentially the energy of a harmonic oscillator. So the energy of the Landau level is the square root of the energy of a harmonic oscillator. This is the reason why in the Dirac equation, we get the square root of b instead of b. The Hamiltonian cannot be easily solved, but the square of the Hamiltonian can be easily solved, and the square of the Hamiltonian is a harmonic oscillator, and therefore the spectra of the Hamiltonian itself is the square root of the spectra of a harmonic oscillator. Let us now look at how the spectra of this problem looks like. So just as a reference, we can take a tie-binding model, and in this tie-binding model, we add a magnetic field using the Peierls substitution. And in particular, you can take a tie-binding model, a square lattice, where the top and bottom of the bands are essentially parabolic. So you hope that when you add a magnetic field to a parabolic band, you will recover the result of the Landau levels that we had for the Schrodinger equation. When you do this, you obtain the band structure that you have on the left. So there's a set of blue bands that are the ones on the left that propagate in one direction. There's a set of green bands that are the ones in the middle. And there's a set of red bands that are the ones that are located on the right of the plot. The color in this band structure corresponds to the location in real space of the wave function associated to that eigenstate. So you effectively have states that are in green that are all located in the bulk and that they are flat. They do not have a dispersion. And then you have states that propagate in one direction located in one edge, and states propagating in other direction that are located in the other edge. The flat states are the Landau levels. The blue and red states are the chiral states of the system they are not captured in the analytic iteration that we did before, but one can derive them by solving that at a finite boundary. So the basic idea is that this result that we got for a continuum model automatically holds when you include the Peierls substitution in a tie-binding model. And the idea is that the Peierls substitution at low energies is equivalent to solving the differential equation that we showed before. So that is the reason why in the square lattice, if you take the chemical potential at the very bottom, so you think that this square lattice is just a semiconductor that has a very, very small number of electrons, then you recover the same result as the one that you have in the continuum model. And of course, this is something that one can do systematically with the library that we are using during the course. So you can, let's say, build your ribbon by yourself, as you see in this slide over here, with a certain width. So with 30 width shown here, you can add an orbital magnetic field. You can add the on-site energy to essentially put the chemical potential at the very bottom of the band, and then you can compute the band structure and essentially recover this band structure that features at the same time flat bands and dispersive edge modes that, of course, are chiral. One can use the very same logic on a tie-binding model that instead of having a Schrodinger equation has a Dirac equation. And of course, one of the models that fulfill this condition is the honeycomb lattice model that shows an effective Dirac equation at the k and k prime points of the ribbon. So these points where you essentially have a cone and a linearly dispersing energy as a function of the local momenta. We can do this also with the library. And for that, you can take, for example, a armature ribbon of a certain width of width 30, shown here. You can add a magnetic field, and you can color the states according to the location where they are in the ribbon. So bulk, top edge, and bottom edge. And when you do that, you essentially get the band structure that you have here on the right. And in this band structure, you can see that there's a set of flat bands that are black here, that are located on the bulk. And then there's a set of edge states that here are red and blue, that they are located, of course, on the edges, and are the ones responsible of the quantization of the conductance in the quantum Hall state. Okay, let us now move on to the many-body wave function of the quantum Hall state, the many-body wave function of a field Landau level. And this is going to be a very important step to understand how fractional excitations can appear in the quantum Hall state. The idea is the following. So now that we know that something like a harmonic oscillator appears in the spectra of the quantum Hall state, we can try to define ladder operators in the very same way as we do it in the quantum Hall state. So we can, in a general gauge, we can define a creation operator, a dagger, that is just a combination of momentum and magnetic vector potential and an annihilation operator. And if you use just the definition of the magnetic vector potential that we have, you can automatically see that this fulfills the canonical commutation relations of a let's say, bosonic operator, which is, of course, what we expect of something that behaves like a harmonic oscillator. Now, the idea is that the Hamiltonian of the quantum Hall state can be actually written just as a harmonic oscillator. So you take the definitions of the previous slide, and you automatically see that the Hamiltonian can be written as a dagger A plus 1/2 for as Vonnegut electrons, of course. And this is an automatic consequence of the Hamiltonian describing a harmonic oscillator. So now what we can do is to work on a very specific gauge. And let us take the symmetric gauge, which is the gauge that has dependence both in the x and y directions. If you have dependence both in the x and y directions, you are retaining some rotational symmetry in your Hamiltonian. And the big deal of this gauge is that in this gauge, you can actually show that the eigenstates are just powers of a new variable that is what we call the complex coordinate in real space. So you can take a coordinate that is x plus I, y, and you can actually show that in this gauge, the eigensets of the Hamiltonian are essentially this set to the mth power times a Gaussian envelope. And so now the idea is that regardless of which power you take for this prefactor of the Gaussian envelope, you will always get a zeroth level wave function. So you will have, you can have a wave function that is, let's say, just 1 as prefactor, or z as prefactor, or z square as prefactor, or z to the third power as prefactor, and so forth. And let me emphasize that the form of these wave functions just comes from the fact of writing the Hamiltonian in the symmetric gauge, making the replacement from real coordinates to complex coordinates, and show that any eigenfunction that only has powers of z and not of the complex conjugate is essentially a zeroth level, Landau level wave function. Now, if you have all this set of zero level wave functions, you can actually think that since they all have the same Gaussian envelope, then any polynomial in Z is also going to be a Landau level wave function. So in general, you can write all the Landau level wave functions as an arbitrary polynomial in Z times the Gaussian envelope of Z. What is important is that you don't have the complex conjugate of Z in this polynomial. If you have complex conjugate, you no longer have an eigenstate, but if you only have set in the polynomial, then you do have an eigenstate. These are, of course, single particle wave functions. So all the wave functions that you write down in this way are just the eigenstates of the single particle Hamiltonian. Now, what we are going to do is we are going to take these single particle wave functions that automatically come from solving the, let's say, quantum Hall state in the symmetric gauge, and show that we can actually write down a many-body wave function for the whole system. So now the idea is that we are going to think about a Landau level, and we will try to write down a wave function where every single state in the lowest Landau level is filled. So a state where every single possible zeroth Landau level has one electron. So in practice, what we have to do is we need to come up with a many-body wave function that has every single zero Landau level wave function, so sort of all the possible powers, and that also fulfills Pauli exclusion principle, so that it's anti-symmetric. And the solution is actually relatively simple, and it's the one that I am showing you here. And I think that it's important just to go through every single component of this formula. So first of all, we have a product over all the coordinates of the electron. So now we think that we have NP electrons. So there's a product of over the coordinate of the electrons. Then we have set I minus set J. And the idea that this term is essentially making the wave function completely antisymmetric. So if you switch I and J, you effectively pick a minus sign, which is what you expect for fermions. This is Pauli exclusion principle. And what is important is that when you do a product of these different sets, you effectively get a polynomial in set. And a polynomial in set was a, let's say, a zeroth Landau level wave function. And then what we have is the exponential of the sum of all the complex coordinates to the second power. And of course, this is the Gaussian envelope that we had before. So if we just make a Slater determinant of all the zero Landau level wave functions, the let's say the exponential part can be multiplied and the exponents can be summed up, and that's how you get the formula that you get over there. So in short, this is the many-body wave function of the field lowest Landau level, and it directly comes from considering a wave function that has all the possible zeroth Landau levels, so in particular all the possible powers, and that it's fully antisymmetric. Now, if you consider a certain number of zero-level wave functions, you can actually see some very interesting property of this wave function. So in general, the wave functions of the zero Landau level were this set to the m times the Gaussian envelope. And what you actually see is that the bigger the m, the further the maxima of your wave function is. So for m equal to 0 is right at the origin, then for m equal to 1 is a little bit further, for m equal to 3 a little bit further, and so forth. And a relatively simple way of understanding this is that you can think that the mth wave function describes an electron that has m angular momenta. And therefore, if you have m angular momenta, you need to be a little bit far away from the origin. This has another important consequence, which is that the higher the m, the higher the area your Landau level encloses. And in particular, the higher the area of magnetic flux you are enclosing. And this is going to be important later on. What is interesting is that if you just consider that Slater determinant from before and you sum all the contributions, what you actually get is that your net wave function has a density that it's almost constant up to a certain radius, that then afterwards it quickly decreases to 0. So the wave function written in that way, up to a certain m, essentially describes a 2D electron gas that has a uniform density in real space, and then at a certain radius, it quickly decays. So you are effectively having a featureless electron gas up to a certain radius, and this will be important later on. Okay, so now we got the wave function of the quantum Hall state, and we got it just by taking the eigenstates of the Hamiltonian written in the symmetric gauge, doing this change of variables with from real coordinates to complex coordinates, noticing that as long as our wave function only has sets and not conjugate sets, then we effectively have an eigenstate. And then we build our Slater determinant with all those wave functions. The idea now is to generalize this to a case where we have fractional filling. So where not all the electrons are, let's say, occupying the zero lambda level, but that there are some states that are empty. And the idea is the following. So let us imagine a zero lambda level that can contain 3 different electrons, 1, 2, and 3. Previously, we just considered that all these electrons were filled, and for that, we just made the product over all the possible single particle states. Now we want to fill only 2/3 of these electrons, but we want to do it in a non-trivial way. Of course, we could just fill one Landau level, another Landau level, and the other one leave it completely unfilled, but that is going to create a density that is modulated in space because each Landau level is located at a different radius, as we saw in the previous slide. What we want to create is effectively a uniform electron gas, so a system that has a uniform density, but that it doesn't have all the levels filled. And this is, of course, a very non-trivial statement, but there's a relatively nice heuristic way of building such a wave function. So what we need is a wave function with a fractional filling. So it has to be a many-body wave function. It should look like a Landau level. So the wave function for the filled Landau levels that we got before may be a very good starting point. It should still fulfill Pauli's exclusion principle because even when we have fractional filling, our electrons are still electrons and they have to give rise to an antisymmetric wave function. And then if we believe that this state actually appears when we have very strong correlations, it would be very nice if our wave function tries to put electrons as far from each other as possible, because this would be the situation that would naturally arise if we have repulsive electron-electron interactions. Electrons would like to minimize the kinetic energy just by staying as far from each other as they can. And so the way to get a wave function like this, it's actually magically simple. You just need to take the wave function of the filled Landau levels, and instead of just having set I minus set j, you put a power there. And the trick is that this power, of course, needs to be an odd power because otherwise your wave function is symmetric. But it has the following properties. If you compute what is the electronic density of this wave function, you effectively have 1 over m electronic density. So instead of having charge 1, you have a charge 1 over m. So you have fractional filling. And the most important property of this wave function that we will see it later on is that if you think about excitations of this wave function, you get excitations that have a fractional charge, that have a charge 1 over m. And let me emphasize how really exciting this is. So you start with the wave function for a single particle system, that is the filled Landau level. You start asking yourself, well, how should I write down this wave function if instead of having a filled Landau level, I have a partially filled Landau level? And just by using some heuristic arguments based on Pauli's exclusion principle, let's say minimizing the distance, minimizing how much Coulomb energy you pay, and trying to look for a featureless electron gas, you get a wave function that gives rise to fractional excitations. There's something very important to notice also about this wave function is that now, if you, let's say, make all the products of all the terms that you have in the wave function, now the maximum power of the wave function is m times n minus 1. And that this maximum power gives rise to a filling that it's smaller than 1, that it's the fractional filling 1 over m. Now, that is the ground state wave function. So that is the lowest energy state of a 2D electron gas that has Landau levels to start with, but that not all of them are filled, and that you fill them so that you can actually, let's say, minimize the electronic repulsion between them. An important question is now, what are the excitations over this wave function? And the point is that one can actually write down the excitations in a relatively simple way by using these complex coordinates that we introduced before. So, for example, if you think about, let's say, having a quasi-hole at the origin, the only thing that you have to do is to multiply by a complex coordinate set. And the reason for this is that when you multiply by set, you are essentially pushing charge towards the outside, just from the fact that the different Landau levels had a charge density that scaled with m. So when you add set, you are essentially just moving the charge outside the origin. And of course, you could create a quasi-hole at a certain location w by multiplying by set I minus w. These are the quasi-particles of the fractional quantum Hall state. And what's important of these quasi-particles is that they have a fractional charge, 1 over n. So now the idea is that when you multiply by this power, as mentioned before, you are essentially increasing the power of all the coordinates of the electrons that you have. And when you increase the power, you essentially push away the electrons that are at the origin. The amount of charge that you push away is exactly this charge of the quasi-hole, this fractional charge. And of course, you can use this very same logic to create several quasi-holes. So you can create one quasi-hole in location W1. You can create another quasi-hole in location W2. And this is going to be important later on. If you create, let's say, m quasi-holes, you effectively just insert one charge. And this is, again, related with the fact that you have fractional electronic excitations in the fractional quantum Hall state. You can, of course, have also quasi-electrons. And the simplest way to figure out how a quasi-electron should look like is by thinking about what is the inverse of putting a power. And in a simplest way, you can think that the inverse of putting a power is removing a power, and you can remove a power by making a derivative. This is a little bit more complicated than what we are stating here, but at our level, let us just assume that if you want to create the opposite of a quasi-hole, you can just remove a power by inserting a derivative in your wave function. And when you do this, you also get, let's say, fractional excitations, but now the fractional excitations have a, let's say, opposite charge. So you essentially pull charge towards the origin. Okay, now let us see how this wave function of the fractional quantum Hall state, that it's called the Laughlin's wave function, allow us to see that we have fractional excitations. And for this, we are just going to use one of the concepts that we saw in the previous lecture. So we are going to use the Berry phase. So now the idea is the following. So we are going to take our wave function of the fractional quantum Hall state, and we are going to create an excitation at location W. And we are going to see what is the phase that our many-body wave function takes once we move the location W around a circle. So you can do this just by first writing down how the many-body wave function in the presence of an excitation is. That just consists on multiplying by set I minus W, then parameterizing your W by absolute value of W times e to the I theta, and then just computing the integral that you have over there for the Berry phase. When you do that, you essentially get the formula that you have at the very bottom. And this is obtained directly by using the many-body wave function of the fractional quantum Hall state. You get a dependence on the total flux. So essentially, the phase that you pick when you move your quasi-excitation depends on how much magnetic field you have inside the trajectory, which is, of course, the Aronoff-Bohm phase. But what is most important is that you also have a prefactor 1 over m. And let me emphasize that the Aharonov-Bohm phase depends on the flux that you have inside, but it also depends on your charge. So the fact that we have an 1 over m here in the very phase is essentially telling us that the charge of our excitation is not 1, but it's a fraction of 1. It is 1 over m. So with that, we know that we have excitations that have a fractional charge, that the electron is no longer the fundamental excitation, but a fraction of an electron is the fundamental excitation. Now let us see that these electrons actually have, or these quasi-excitations actually have very interesting statistics. So now the idea is that instead of just considering that we move one quasi-hole around the origin, we are going to take a many-body wave function that has one quasi-hole in the origin and one quasi-hole at a certain location W. And what we are going to do is we are going to move one of the quasi-holes around the other quasi-hole. So we take the wave function that has these two excitations. We parameterize again the location of the quasi-hole as absolute value of W phase times the phase, and then we just put it in the definition of the very phase. And if you do the integral, what you actually obtain is that the very phase has now two components. One component that it's the Aharonov-Bohm phase, that it's proportional to the enclosed flux times the charge, that is the same as what we observed before. And then there's another phase that it's called the statistical phase. This is essentially the phase that we get from exchanging these two excitations. And this phase is actually 2 over m. It is not the phase of a fermion, it is not the phase of a boson, but it's the phase of an anion, which is a quasi-particle that is different from both bosons and fermions. So we started with a many-body wave function for electrons, for fermions, and we end up with a many-body excitation that it doesn't behave like an electron, and it doesn't behave like a boson. This is one of the simplest examples of fractionalization in quantum matter. Okay, and now to finish, let us try to make a step back and see how the quantum Hall state is related to Chern insulators, and in particular, how we can have a very nice equivalence between quantum Hall state and Chern insulators. So the idea is that so far we focused on looking at systems that have a net magnetic field. So we got a two-dimensional electron gas and we applied a magnetic field. We got Landau levels. We wrote down the many-body wave function of a Landau level, and we got even to the fractional case where we had fractional excitations. Of course, to have quantization of the whole conductance, we do not need Landau levels. We could have a very special electronic structure that has bands, that breaks temporal symmetry, because of course, to get a fractional quantum Hall conductance, we need to break temporal symmetry, but it doesn't have a net magnetic field. And the idea is that you can take some bands, and those bands may have some finite Berry curvature, and when you integrate the finite Berry curvature, you get a finite Chern number, and this finite Chern number is essentially the one that gives rise to your quantized conductance. There are, of course, many models that have this property, but maybe one of the most popular ones is the so-called Haldane model. So the idea is that you start with a honeycomb lattice. You effectively have just sites on a honeycomb lattice, and you include both first and second neighbor hopping. And the second neighbor hopping are chosen so that they are imaginary, and in particular, the break temporal symmetry. So when you do the Fourier transform of this Hamiltonian, when you write down the block Hamiltonian of this Hamiltonian, what you actually get is that the imaginary second neighbor hoppings appear in the diagonal of your Hamiltonian as a mass. And this mass changes signs between one valley and the other valley. And this changing sign between valleys gives rise to a finite Chern number in the electronic structure, and you end up with a model that has no net magnetic field, but it has a finite Chern number. And you can see this relatively easily with the computational exercises. You can take the electronic structure of graphene, you add a Haldane coupling, which is the second neighbor imaginary hopping, and then when you compute the Berry curvature, you see that the Berry curvature takes the same sign both at value k and at value k prime, and therefore once you integrate it in the reciprocal space, you will get a net Chern number. And of course, the consequence of this net Chern number is that when you look at the surface of your material, you are going to see that there's one chiral edge state, which is the state that is responsible for the quantization of the whole conductance. And when you look at the bulk of your material, you are going to see a gap. And of course, this makes your system a bulk insulator. If you look instead of to a ribbon, what you actually get is that you have, let's say, simultaneously in your band structure, the bulk states and the edge states. And in particular, you have one edge state that it's on the top that propagates in one direction and another edge state that it's on the bottom and propagates in the other direction. Now, once we have a ribbon, we can start asking ourselves, how is this edge state actually connected to the edge state of a quantum Hall state? And the idea is that we can now just make an adiabatic connection between the Chern insulator that we have in the honeycomb lattice and the quantum Hall state that we have in the absence of a second neighbor imaginary hopping, but in the presence of a magnetic field. So we start with the Haldane model. We start with our model with an imaginary hopping. We can switch on a magnetic field. And when we switch on a magnetic field, we effectively get our Landau levels and flat bands. And now after, we can just switch off the Haldane coupling. So when we switch off the Haldane coupling, we just end up in the quantum Hall state. And you see that in this whole process, we didn't close the bulk gap. So the gap in the bulk was always open. The edge states were always present. So the two systems are topologically equivalent. So this is a quite theoretical way of seeing that the Chern insulator of a quantum Hall state, and in particular in the honeycomb lattice, is actually topologically equivalent to a conventional quantum Hall state, because you can connect both systems without closing the gap in the bulk. A last important point is that Chern insulators, of course, can be observed in nature. So there are materials that show a quantized Hall conductance even at zero magnetic field. And there are two very popular examples. One is the case of magnetically doped topological insulators, in particular chromium dope bismuth telluride. And there's another example, which is the case of twisted graphene bilayers. So these systems break time reversal symmetry intrinsically, the first one due to magnetism, the second one due to orbital currents, and this breaking of time reversal symmetry gives rise to topological bands that have a finite Chern number and therefore quantization of the conductance. One can actually have also materials that show fractional quantum Hall state at zero magnetic field. And the trick is that there are some materials that feature flat bands and that these flat bands are topological. And this is the case of twisted two-dimensional materials. So many of these materials feature flat bands, and the mathematical structure of the flat bands comes from an artificial magnetic field that is essentially associated to the elastic modulation in real space. And in particular, one of the most important materials that features this fractional quantum Hall state is molybdenum ditelluride bilayers that were, let's say, very recently discovered. So just to summarize, if I could ask you to remember something, please remember that the quantum Hall effect can exist both with and without external magnetic field. Today, we focused on the case with magnetic field, and we understood that the spectra of the quantum Hall state is related with Landau levels, which are effectively, let's say, harmonic oscillator levels. They are flat bands, they are topological, they have a finite Chern number, and in particular, when you take these Landau levels and you put a fractional filling of electrons, you get a many-body wave function that has fractional excitations with fractional charge, and they have non-trivial statistics when you write them. Thank you so much for your attention.